Hello everyone. In this video, we're going to be starting the section 11.3, or also the integral test and estimate of sums. So in the last section, we learned how to work with series, especially geometric series and the divergence test. Now, we're going to be learning a new test called the integral test. And basically, the main idea of the integral test is that we can decide whether a series converges or diverges by testing an improper integral instead. So instead of working directly with the series, we're going to match it to a function, check a few conditions, evaluate an improper integral, and then use the result to make a conclusion about the series. So that's basically like the rundown of what we're going to be doing. So now let's start with the main concept. So our main concept, so let's say we have a series and suppose the terms come from a function. So the terms are going to be coming from a function, we'll call that f of n. And the integral says that if the function, f of x is continuous, positive, and it's decreasing, for x greater than or equal to 1, then the series and the improper integral either both converge or both diverge. So basically, if the improper integral converges, the series will also converge, and if the improper integral diverges, then the series will also diverge. So this is the main concept for now. We will be exploring this more in detail later in the video. So now let's look at the notation and theorems you need. So as you've been knowing from the past videos, the series notation is always the same. It's just going to be your sigma, your terms. So this is just a series. And then you're going to have a function connection, so that is just your a sub n will equal f of n. And what this means is that the terms of the series, so a sub n, comes from plugging in the integers to a function, which is f of n, the function of n. And then we're going to have an improper integral we're going to compare to. And the improper integral looks like this. So from 1 to infinity of f of x. This is what we're going to be comparing with the series. And then we have the integral test. So let's write it down. So if f is continuous, positive, and decreasing, on 1 through infinity, and if your a sub n, your terms are equal to the function, then your series and your improper integral either both converge or diverge. So that is basically all that it's going to be for this video. So I'm going to have a series. We're going to see if the terms match the function. We're going to just check the 3 small conditions, evaluate the improper integral, and we'll know from there whether it converges or diverges. So I guess to make it seem like you guys feel better, this is probably one of the easiest tests you will have compared to what's coming next. So not to scare you guys, but also give you guys hope that this one is not bad. So basically all this is saying is that series and integrals behave the same way as long as the 3 conditions are true. So now we're going to be looking at when to use the integral test. So this is important because I just taught you what the integral test is and everything, but you're like, how do I use it? Well, you should think about the integral test in these. So I'm going to write some bullet points. I would write it down. So the first thing, let's say, is the series or the series terms look like they come from a function. Which we write that as f of n. And then if the function is easy to integrate, and you know if the function is positive, continuous, and decreasing. These are like the 3 conditions we have to check. So some common examples of what it would look like that you would use these would be like, look something like this. So let's say you had series of 1 over n to the p, or so these 2 are like common examples because p is just an exponent, right? Like power could be anything. And you know that whenever something is 1 over something, you already know that you're checking the decreasing thing because anything over 1 is just decreasing. You know it's positive because the exponent at the bottom, like let's say you had n to the p, so let's say you had n to the 200, you know it's positive, you know it's continuous. So these are like common examples to look for that you will be looking at to determine whether if this is when you use the integral test. Now, before we go to examples, we're going to see a step-by-step method on how to use the integral test. So let's start with step 1. It's always going to be to write the series clearly. Then we have step 2. We have to identify the function. So f of x, so that the terms are equal to the function. Then step 3 is to check our 3 conditions. Which are just going to be positive, continuous, and decreasing. And then step 4, it's going to be to write the improper integral. Just remember, it's just from infinity to 1 of f of x. And then slash, I guess I'll just write slash evaluates the integral. And then lastly, step 5 is just use the result to conclude. So if your integral converges, that means your series converges, and the opposite. So if your integral diverges, that means your series also diverges. So this is like the step-by-step, I guess, method of how you can solve any integral test. Sorry, any series with an integral test. So now let's start with the examples. So now let's look at example 1. It says, determine whether the series, I'm sorry, that does not look like series. It's a bad handwriting. There we go. So determine whether the series 1 over n squared converges or diverges. So, well, we don't have to really write this out clearly because it's already written out. So remember? So let's identify the function. So we know that the function, or the terms right here, is just 1 over n squared. So where's our function going to be? Well, it's just going to be 1 over x squared. Because when you plug in x equals n back to the equation, so when x equals n, you're going to get f of n is equal to 1 over n squared. So basically, just to make this less complicated, whenever you want to go from a term to a function, just replace the n with x's. That's like all you have to do. But that's how the book says it, so that's how I'm writing it, so just in case. But yeah, you're just going to replace the n's with x's, and you can always plug it back. So I'll erase this, but you can write it down if you want to. So we found our function, and now let's check the conditions. So the first thing, remember, if it was continuous. So is 1 over x squared continuous? Well, we know that 1 over x squared is continuous for all of x that is not equal to 0. Because you know when it's 1 over 0 squared, just 1 over 0 on the bottom, that's undefined. So, however, in this integral test case, we only check from 1 to infinity. So this is continuous for x greater than or equal to 1. So remember, just because that 0 isn't included, 0 makes this continuous, don't just think like, oh, you can't use integral test. Remember that the condition states that it has to be continuous from just any number greater than 1, greater than or equal to 1. So now let's check. Is 1 over x squared positive? Well, we don't have to look at the 1, so let's look at x squared. So we know that x squared is always greater than 0. Therefore, it is going to be positive. So actually, we'll just write positive for we'll just write from 1 through infinity, the bound. And is this decreasing? Well, we know that whenever it's like it's like 1 over anything, it's going to be decreasing. So we know that as you plug in more values for x, it's just going to get bigger and bigger. You know, 1 divided by a big number is just going to get smaller and smaller. Therefore, this is decreasing. So it gets smaller as x gets bigger. Therefore, as you can see, we met all 3 conditions. So the integral test does apply. So now I'm going to erase this, so if you want to take a moment, you can pause it really quick. Now, our next step is to write the improper integral. So now we're just going to write the integral. It's the integral from infinity to 1 of f of x dx. We're going to replace that with the f of x that we have right here. So this just becomes the integral from 1 to infinity of 1 over x squared dx. Now we're going to evaluate this step by step. So the first thing that you should know how to do when you see 1 over x squared or just exponent at the bottom is always to move it to the top so it's easier to integrate. So you know that 1 over x squared can be rewritten as x to negative 2. So to bring it up, you just flip the sign of the exponents. So you get is equal to of x and negative 2 dx. Now, you should know from your earlier units in calc that this is an improper integral, so you do have to rewrite this as a limit. So how do we do that? We're going to rewrite this as the limit. Remember, we use the term b as b approaching infinity of from b to 1 of x to negative 2 dx. Now we integrate, so we're going to add 1 to the power, then divided by it. So negative 2 plus 1 is just negative 1, and divided by negative 1. Therefore, you're going to get that this is equal to just negative x to negative first power. So let's rewrite this back. So we're going to have the limit as b approaching infinity of, I like to write this in boxes because it's easier, of negative x to negative 1 from b to 1. So now you're just going to plug in the bounds. But before we do that, I kind of like to rewrite this, the negative x and negative 1. So this can be rewritten as negative 1 over x. Remember, to move the x from top to bottom, you just flip the sign. So it'll become x to the first, but you still have a negative on the outside, so that's going to transfer to the negative 1 at top. So now we can plug it in. So we'll have the limit as b approaching infinity of, let's plug in a b first, so it's going to be negative 1 over b minus negative 1 over 1, which I'll just write as negative 1. So let's just factor this negative sign in. So we get it's going to be, so I'm going to move this, since it's a positive 1, I'm going to move this to the front, so it's like makes it cleaner, so 1 minus 1 minus 1 over b. Now we can just take the limit, so the limit is b approaching infinity of 1 minus 1 over b is equal to, remember, we've plugged in an infinity for b. A small number of a huge number is 0, so what's 1 minus 0? It's just 1. Therefore, the improper integral converges. That's the answer. So, the improper integral converges. So, since we knew that the integral of 1 over x squared converges, the series will also converge by the integral test. So, on your homework or test, I would write the improper integral, I can't talk, I'm sorry. The improper integral converges by the integral test. Or you could also write the series also converges by the integral test. So, your final answer should be like, just rewrite the series, 1 over n squared converges by the integral test. And that's all you have to do. Now, let's look at another example. We have determine whether the series 1 over n converges or diverges. If you remember from last video, I believe, I told you that this is also called the harmonic series. So let's write out the terms. First step. So we know the term is just 1 over n. Now, let's identify the function. Remember, we just replaced the n's with x's, so the function is just 1 over x. Now, let's check the condition. So, is 1 over x continuous? Is 1 over x continuous? So, kind of like the last example, this is continuous for all x that doesn't equal 0. So luckily, we're lucky that we don't have to deal with 0. We only need to worry about from 1 to infinity, so we can put a check. So it is continuous. Is this positive? Is 1 over x positive? Well, for x is greater than or equal to 1, this is positive, which is all that matters. So, yes. Is this decreasing? Well, we know as x gets larger, 1 over x gets smaller. Right, same idea as last time. As you plug in bigger and bigger values for x, well, a small number, or sorry, a small number over a big number is going to start decreasing. So all 3 of these terms applies, so you can do the integral test. So I'm going to erase this. Let's start integrating. So now we just write the improper integral. So we know it's just going to be from infinity to 1 of 1 over x dx now we can just rewrite the limits. So this is also, or I'll just write equals the limit as b approaching infinity from b to 1 over x dx. So now we can integrate. So as we should know, the integral of 1 over x is just the natural log of x. So let's write down here, the integral of 1 over x is equal to the natural log of the absolute value of x. Therefore, this is just going to be the integral from 1 to b of 1 over x Oops, I forgot the limit sign. Whoops. Sorry, I'm running out of room, so I'm trying to write small. I'm going to evaluate this from B1 to B. So now we can plug in the bounds, right? So this is going to be the limit as B approaches infinity of natural log of B minus natural log of 1. You could get rid of the not the natural log. You could get rid of the absolute value signs because you know they both are positive, but I don't know, I just kept them. So we know that natural log of 1 is equal to 0. Therefore, we're going to have, so the limit is B approaching infinity, which is going to be equal to the natural log of B. Well, B is infinity, and the natural log of infinity is just infinity. So we know that and we know when it's approaching infinity, it diverges because it's not going to a single number. It's just increasing forever and forever. So this is how I'd write it on a test or a homework problem. So I write it in blue. Since the integral of 1 over x dx diverges, the series also diverges by the integral test. So that's all there is. Now let's just do a recap. So remember that the theorem was that if f is continuous, positive, and decreasing on 1 to infinity, and your term is equal to the function, then if the integral converges, then the series converges. However, if the integral diverges, the series diverges. So just make sure you check the conditions, and if they're all satisfied, you're ready to use the integral test. And remember that you should use the integral test when a series comes from a function. The function is easy to integrate, and the function is positive, continuous, and decreasing. So basically, just identify your function, check for your 3 conditions, evaluate, and use the result to conclude about the series. So that's all there is for the integral test. And if you have any questions, if you have any questions, you can leave them in the comments. Other than that, thank you and have a great day.